to go over here. I'm going to open this. And now we're ready to go. So this is the first in a series of videos that I want to put together that are going to be at the end of every chapter that we're going to have. And the idea behind these videos is that they're meant to help you reflect on some of the things that we've done. So they're going to lay out the tools that we used in the chapter, in this chapter in particular, our general tools, some tips that I have for you, and some pitfalls and some places where you might have made mistakes that you want to think about the way that you're applying the tools to make sure that you're not making any mistakes. Okay, so the first thing I want to do is to lay out our tools again, because when I first did this, it was in a very abstract sense. We didn't have anything to apply it to, but now that we've been working on some problems, it's worthwhile to reflect on them, to think about the way that we are applying these tools to the physics that we're trying to do. And so you remember the first tool that we had was our imagination and diagrams. So when it came to one-dimensional motion, we could think about how an object is going to move in one dimension. What diagrams can we draw to record that? We also talked about words. What words are we using to describe that situation of something moving in one dimension? We talked about scaling arguments and numbers. So if I plug some numbers into an equation, is that going to give me something that's going to be too large or too small? If something's going way faster than I expected it to be, or way slower, or something takes longer than it should. Those are all this kind of scaling arguments and numbers that we talked about in our general description of tools. We also have been using a lot of symbolic representations in algebra, and this is going to be probably one of the more difficult things to get accustomed to, but as we go through the semester and you use it more, you're going to realize that the symbolic representation is actually one of the more powerful tools that we have. Dimensional analysis and the equal sign come into play because we want to say, okay, if I have some kinematic equation that I'm plugging some numbers into, or I derive a kinematic equation, do the two sides of the equation agree with each other in terms of the units? And the way that we did that was to apply dimensional analysis. We also talked about plotting. So when we talk about the motion of an object in terms of the kinematic equations, there's an associated plot that we can draw. And the plot gives us some additional insight into what's going on, and it feeds back into all of the rest of the tools that we've laid out here. We also introduced calculus. So between calculus and algebra, these are probably the two most difficult tools, and maybe the ones that you don't use as frequently, but these, or hadn't used them as much before. But again, these tools all feed into all of the other tools, and all of these tools have to work together in order to get you the right answer when it comes to trying to talk about one-dimensional motion in this case. And then there are two more tools that we're going to introduce in the next chapter. These are trigonometry and vectors. And then that's actually all of the general tools that we have. Everything else from there is just applying the relationships between physical quantities. So what's the relationship between force and mass and acceleration? All the other tools that we need to talk about those situations we already have. We're just going to be getting more and more practice with them. Okay. Okay, so there are some chapter-specific tools I'd like to talk about, and this is, like I said, what we're really going to be getting into more as we move on. So the first tool is understanding the definitions of position, velocity, and acceleration, and their relationship when it comes to the calculus. And so you'll note that I've been drawing this chart over and over again when I'm doing my work to show their relationship in a visual way. So you have your acceleration at the top, velocity in the middle, position at the bottom, and how you go between these, and what the relationship is between the velocity and the position, and the velocity and the acceleration. You want to, if there's something to memorize, that's the thing. And then when you memorize it, think about, well, why is the chart made the way that it is? It's really representing a lot of information in a very succinct way. That's the real power of that chart. Okay, what does it mean to turn around? That's another important thing, and something that maybe I didn't discuss very explicitly, but when we were talking about that problem where the rock is going up, it's turning around at its maximum height. And so what it means to turn around is to have a velocity of 0. Or you could say, equivalently in the language of calculus, that the time rate of change of position is 0. So when I get up here, the position's not changing anymore. It's gotten to a position, it stops at that instant when you're evaluating at that particular time. Okay, one last tool for the physics. What does it mean for two objects to intersect each other or to collide? That means that they're going to be in the same place at the same time. And we talked about the ways that we can represent this mathematically. Okay, so now we have all of our tools laid out. Let's talk about some tips. Okay, so the first tip is recording your thought process. This is what goes under the umbrella of show your work. I'm not always the biggest fan of that verbiage because it conjures up memories of high school and middle school teachers like yelling at me for not showing my work. But this is really more important than showing your work. Recording your thought process allows you to go back and ask yourself if something is consistent or not. And it additionally allows us to give you partial credit, because if you have something wrong and there's no thought process recorded, there's not a lot of way that we can kind of give you the benefit of the doubt and say, well, maybe they were thinking this or maybe they were thinking that. We really need to be able to see what the thought process is. And so recording your thought process is really important. Try to record as many steps as you can when you're doing this. It'll help you when you're going back through and checking for consistency. That's another tip that we'll talk about in a second. Reread the question. So a lot of times you'll read the question really quickly and then start working, but read it, ponder it, think about what it's saying, and then start working. Or if you reach an impasse, reread the question again. There might be some additional information that you missed the first time that you read it that's going to help you moving forward once you discover it. Okay, so that's rereading the question. Ask yourself if there's a better way to do the problem. So a lot of times you'll end up beating your head against the wall because you know, well, this way is going to work, but it's really hard to do it like that. So sometimes you have to kind of take a step back and look at it and say, well, maybe there's a better way to do this. That's another tip. Look for consistency. This is one of the most important tips that I can give you, and it's in some ways it's really a tool. It's really the application of the tools that we have. So looking for inconsistency is how you're making sure that you're not making any mistakes. So when I say look for inconsistency, I'm talking about checking equal signs, making sure that the left-hand side and the right-hand side say the same thing in terms of the units, making sure that the equations are telling you what you expect them to. So you have some expectation about what should be happening. Are the equations actually telling you that or not? Do those equations match the plots that you're drawing? There's so many levels of things that have to say the same thing. You'll realize a lot of times that you're making a mistake if you're looking back at what you've done already. And again, this is why recording your thought process is important, so you can look back at what you've done already. And asking yourself, is everything consistent? Okay, so looking for inconsistency is very important. Start from first principle. So a lot of the things that I'm going to be doing in our section in particular is going to be starting from first principle. And the reason why I do that is it helps you build connections and understand like how all of these tools really work together. And ultimately, you're going to be able to do more if you do that, as opposed to just starting with an equation and plugging things into it. Because a lot of times what ends up happening with students, and I'll talk about this in the pitfall section, you'll pick an equation that's not applicable. And the reason why you're picking an equation that's not applicable is you think, okay, well, it has all the quantities I need in it, I think. But without understanding where it came from and how it connects to first principle, there's opportunity to make mistakes. So always try to start from what's the most true thing, the thing that's always true in general, that's really going to help you in the end. Put the pencil down. So we're kind of trained, and I've been away from it long enough that I've kind of gotten away from this, but you guys kind of might still be in this state where, you know, going to college means you had to take an SAT, you had standardized tests in high school, you had to do things quickly and accurately. Physics is not a standardized test like the SAT. Physics is slow sometimes. Sometimes you have to stand back and look at what you're doing and then think about what you're doing, as opposed to just saying, I'm here, I need to get an answer, I have to go there as quickly as possible. So sometimes what you need to do is use the tools. Put the pencil down. Pencil's a tool, but you know it's not the only thing you should be using. Put the pencil down, think about what you're doing. Try to verbalize it to yourself. And then pick the pencil back up again once you've kind of got your bearings. You don't have to just rip through an entire problem on paper. I certainly don't do that. And most people that are really good at this don't do that either. Okay. The last one is start early and walk away. So we give you a timetable for a lot of the things that we need you to get done for a given class. But try not, and this is something that's hard for me to say, and I'm somewhat hypocritical in saying this, try not to procrastinate. And even if that means you're not really starting an assignment or you're not putting pen to paper yet, if you read it and you think about what it is that you're going to have to do, things will occur to you sometimes as you're going out through your day, or you think about it for a while and say, huh, I wonder how that works. You might be in the shower. This happens to me all the time. If I'm working on something and then I go and do something else, it occurs to me that like there was a piece that I was missing. And if you start early, and like I said, you don't even necessarily need to start solving problems, but if you're reading them and you're thinking about them, and then you walk away from them, things will occur to you over the course of your day. I'm sure that's something that's happened to you before. Okay, now we've gotten our tips. Let's get into our pitfalls. So there's two big mathematical pitfalls that I want to address, and then we'll talk about the physics pitfalls that are specific to the chapter. The first one is algebra mistakes. And algebra mistakes always characteristically have the same problem. It's the fact that equal signs are not matching, or that you've carried something over from another line that is not consistent, okay? So this is where dimensional analysis is your friend, because the physics and the dimensional analysis is informing you what the algebra needs to say. And you can check this line by line and say, okay, well, is this physical quantity what I expect it to be? This should be a position. Why do I have a time on this side? Something went wrong with my algebra. Let me go back. I recorded my work. I can see then where it is that I might have made a mistake, and then I can fix it and then move forward. You should, in thinking about these problems, it's not a linear thing that you're doing. And remember the math magician, what did he keep doing? He'd pause. He'd look back at what he'd done already, made sure it was right before he moved on. It's something that experts at a lot of things, not just math and physics, but experts at a lot of things will constantly be checking themselves, making sure that something's correct before they move on, because they realize that fixing it later is going to waste more time than pausing for just a moment to look at it. And they get really good at looking at it quickly and saying, is this what I expect it to be? This is why it might be, this is why it might not be. Okay, I can compare those two things. It's definitely right. Let's move on. It's a really important and powerful tool to use. And this is all feeding into the umbrella of looking for inconsistencies. You'll be able to do a lot better on these things. Again, if you don't look at this in a linear fashion, you kind of start moving, you look back up, and then you keep going, you look back up, and you keep going, you look back up, and then you might pause and look further up, right? So, like I said, when I solve problems, that's what I'm doing. I'm not point to point, just go. And you'll realize, like I said, when people get really good at these kinds of things, they're doing that. They're going back, they're looking at what they're doing, checking for inconsistencies. Okay, calculus mistakes. So calculus is new to a lot of you guys, and there's some things that you might do initially, but I want to point out a couple of things that you might be doing, just so you can, as you're looking for your inconsistencies, try to spot these things that'll help you in the end. The first one is leaving off a dt. So when you're doing an integral, it's always important to include what you're integrating with respect to. And at this point, this might not seem like as big a deal, but later on when we're talking about things like the ideal gas law, to get to one of the most complicated things that we're going to do, or Bernoulli's equation, these are all things that have a lot of pieces in them. And you want to make sure that when you're evaluating the integral, you're taking a derivative, you're doing it with respect to the correct variable. So early on now is the time to catch missing dt's or whatever infinitesimal you're integrating with respect to. It'll help you a lot later, I promise. The next one is integrating incorrectly. So there are rules to do integrals. I'm not going to derive them for you, but they come from your calculus class. And there's only one type of integral and one type of derivative that I'm going to ask you to do. They're powers. So as long as you have those powers down and you practice them a little bit, you'll be able to nail your integrals, and you'll be able to do it correctly. But again, it takes some practice, and you check yourself as you're going. Okay. no constants of integration. A lot of times people will just completely drop the constants of integration. And there are times in the physics that you're motivated to do that, but I would always say write them in first and then reason through why you don't need them, okay? The next one goes along with no constants of integration, and it's assuming what the constants of integration are. So sometimes, and a lot of times, you'll have some V0 or you have some X0. A lot of times people will assume that that's always what the constant of integration is. It's not. You need to make sure that you're looking at the situation that we have and making sure that the constants of integration are actually matching the situation that we're describing. They're recovering all of the correct information that we have in the statement of the problem. Okay, so we're almost through. I'm trying to make this one a little bit shorter. The last one is chapter-specific pitfalls, things that are related to one-dimensional motion that you want to try to spot in your work. The first one is wrong notation. So you'll see throughout the semester that there's a lot of different notation that we're going to be using. I'm going to be introducing vector notation very soon. But every symbol that I'm writing is shorthand for something. Everything's there for a reason. It's not superfluous. It means something. And so when I talk about meaning something, what I'm saying is it's making the equation short, because the equations are like the most succinct thing that we have, right? It describes the situation very quickly and accurately, but that expands out into this whole region of words that we're talking about. And this is how those two tools are really connected to each other, is the notation. So if you ever have any questions about notation, sometimes I forget myself that you guys don't know the notation. I'm very used to it. But if you need clarification about notation, ask me, because it's really important that you understand why I'm using a symbol the way that I am. Like with the example that we did in class, the t versus the t max, the distinction between t as a variable and t max as a value that variable takes when you get to the maximum height, right? That's one of the things I'm talking about with notation. And we're going to see as we go on, we're going to add a little bit more notation as we go, but every time that we add notation, there's a good reason for it. So ask me if you have any problems or difficulty with understanding notation. It really carries all of the physics. Another really common one is saying that the acceleration is 0 when you're turning around. So for instance, if, again, to go back to this same example, you throw the rock up in the air. A lot of students will say that the acceleration is 0 at the top. But think about what it means if the acceleration is 0. If the acceleration is 0, the velocity is not going to change, right? So I get up here, and then if it stops, it has 0 acceleration, nothing's going to cause it, it's not going to move at all anymore. It just stays there. The acceleration is what changes the velocity. So really what's 0 at the top is the velocity, right? Not the acceleration. So if that's a mistake that you might have caught, try to correct it before we get to some of the more complicated material in two-dimensional motion. The last one is using an equation that isn't true. So this is going back to what I was talking about when it comes to consistency and going back to the first principle. Think about the things that are always true. The box that I drew, going up the ladder, going down the ladder, dv dt, dx dt. Those things are the things that are always true. A lot of times you'll kind of pick and choose equations because they fit they'll fit the physical quantities that you want, but that equation isn't applicable in the situation. So go back to first principle, derive those equations, understand specifically what circumstances they're true in, and then if you want to use an equation sheet, and I do sometimes I'll just kind of pull out an equation because I know where it came from, then use it when you know really where it comes from and when it's true and when it's not true. Okay, and so that's going to be it for this one. I hope this series is going to be helpful. So if this has been helpful, let me know in the feedback channel in the Teams page, and I'll make sure to do some more of these. Other than that, I'll see you guys in class. Take it easy.